Hello students, you are all welcome to a YouTube channel Physics for Everybody. Today our topic of discussion is elasticity and it's under the branch of physics referred to as mechanics. My name is Adeboale Jimo and by the end of this lesson you'll be able to state Hooke's law and you'll be able to solve IGCSE past questions on elasticity. Let's go straight to what we have to do today. What is elasticity? Elasticity is the ability of a material to return to its original shape and size after being deformed by an external force. Rubber and springs are elastic material, while plastics are considered inelastic material. What does that simply mean? That simply means if you have a spring and you apply a force to the spring in order to cause it to extend, if you pull the string, it would expand, okay? Why? Because the spring is an elastic material, okay? So that will cause it to expand, okay? Yes, so that's what happens when you pull a string, okay? And if you leave the spring, then it will return to its original shape. It will return to its original shape, okay? And that is common to every elastic material. Another one is rubber band. If you take rubber band and you pull it at both ends, what happens? The rubber band will extend. There will be an increase in length, though it will become narrower, but it will increase in length. And by the time you release the rubber band, then it will shrink again. It will shrink and return to its original. It will shrink and return to its original shape. Why plastics are not elastic? Because you cannot pull plastic and make it to expand. So that is what we mean when we talk about elastic material. Okay, and so while I'm talking about elastic material, there is a law that was propounded by Hooke, and Hooke's law states that the force acting on an elastic material is proportional to the what? Is proportional to the extension produced, provided that its elastic limit is not exceeded. What does that mean? If you want to state this Hooke's law mathematically, you have that the force is proportional to the extension produced. Okay, so from this mathematical relationship, we can simply say F is equal to KE. Okay, so by the time you are removing this symbol of direct proportionality, then you have to introduce a constant of proportionality K. That is where this K came from. Okay, so when you introduce a constant K, then you don't have to put this sign of direct proportionality anymore. So F is equal to KE, that's the mathematical expression of Hooke's law. Now, if F is equal to KE, that simply means we can have a visual representation of this formula as follows. We have F here, then we have K on the left hand side, which is the stiffness of the spring. Then we have E. Okay. From this formula, if you want to make K the subject of the formula, to make K the subject, we divide both sides by E. You know, since F is equal to KE, if we divide both sides by E, so E will cancel out this E here. Let me do that again. So if you divide both sides by E, what happens? E will cancel out this E here. So what will you be left with? You'll be left with K. That simply means K is equal to F divided by E. Okay, good. So from this, we have to talk briefly about K, where K is the what? K is the stiffness of the spring. K is the stiffness of the spring, okay? Or you just say K is the stiffness of the elastic material. Okay, so K is referred to as the stiffness, okay? K can also be referred to as the what? K can also be referred to as the elastic constant. Elastic constant. K can also be referred to as the force constant. Force constant. That is it. So K is the force constant and is referred to as the force that is needed to produce unit extension. Now, what is the SI unit of K? Yeah, so since K equals to F over E, what's the SI unit of K? Its SI unit is Newton per meter. Why? Because force is measured in Newton and extension is measured in meter. Okay. Okay, there are other ways you can state this SI unit. The extension can also be measured in centimeter or millimeter. That's why you can state the SI unit of K as Newton per meter, or you state the SI unit as Newton per centimeter. You can as well state the SI unit as Newton per millimeter, Newton per millimeter, depending on the value of the extension. Yes, so the SI unit of the extension given to you in the question goes a long way in determining the SI unit in which you state the value of K. So this is what we mean by Hooke's law. According to Hooke's law, if you have a spring, okay, that has not been subjected to any force. So in this case, this spring has not been subjected to any force. Okay, so that means here you can say the force on this spring is 0. So here the force on this spring is equal to 0 Newton. Okay, the force on this spring, we call it F Newton. The force on this spring is F. Okay, while the force on this spring is F prime. So what do I mean by the force? The force talks that when you say the force on this spring, we are talking about how much load has this spring been subjected to. So let me just divide this into 3 so you can distinguish between each of these. This is the first case, the first scenario. This is the second one. Yeah, and this is the third one. Now, in the first scenario, you have the force being equal to 0 Newton. In the second case, the force is F Newton. And in the third case, the force is F prime Newton. Why did I say all of this? Now look at this. In the first case, the spring is subjected to a force of 0 Newton. That means the length you have for the spring from here to here is the length of the spring. Yeah, from the topmost part to the lowest position. Let me put it here. From here down here is the length of the spring. And the length of this spring is L subscript 0. That means the force, the length when no force has been applied on the spring. Okay? Now, how do you get extension? Extension of a spring is the difference between the length and the initial length. Okay, when we say E, which is the extension, is the difference between the final length and the initial length. Now, in this case, when the spring has not been subjected to any force, the extension is equal to 0 because the length has not increased. L subscript 0, which is this, is the length when the force applied to the spring is 0 Newton, when no force has been applied. Okay, that means there is no extension. Now, in the second scenario, in the second case, what do you have? You have the force applied is F Newton, right? And what about the length of the spring? The length of the spring has increased. Yes, there's an increase in the length of the spring. So you can see what we have here shows the extension. Okay, what we have here shows the extension. That means the spring has extended. There's an increase in length, right? Good. So in this case, how do you get the length? Let's start by getting the final length. From here down here is the length L1. That's the first scenario. Now in this case, the extension here is equal to what? L1 minus L0. And that is what the diagram shows. You can see this E for extension between BC. That E shows the extension, that's the increase in length, okay? That's how you get the increase in length for the first scenario. And in the second scenario, how do you get the increase in length? Take note that from the top to bottom of it is called length L2, okay? That is the case when the force applied is F prime, okay? Yeah. Or you may call this the force F1. You may call this the force F1, while the other one becomes the force F2. Okay, so that might be an easy way. Let's remove the prime here. So that might be an easier way to talk about it. The force here is F1, the force here is F2. That's the second scenario. The third case, yeah, when a second force is applied. So here, how do you get the extension? Let us call the extension here E2. Let me increase the length of this line. So the extension here is what? L2 minus L naught. Okay, so we can call this our extension E2, okay, between B and D. So that is what happened. As you continue to increase the force, the extension continues to increase, okay? In the first case, no force is applied, okay? The force applied is 0 Newton, so there's no extension. In the second case, there's a force that has been applied due to this mass M. Due to this mass M, a force has been applied, so there's an extension. In the third case, a bigger force is being applied, so that makes the spring to extend by a bigger amount. That's why E2 is bigger than E1. So from all of this, you see that according to Hooke's law, if you decide to plot a graph, of extension against the length, sorry, a graph of extension against the load in Newton, you can call the load the force. If you plot a graph of extension against the load, let me clean this so I can write extension here. Good. So a graph of extension, let our extension be in centimeter. A graph of extension against load will give you a straight line graph that passes through the origin 0. Okay. Why? Because when the load is 0, the extension is 0. When the load is F1, the extension will be what? The extension will be E1. When the load is F2, the extension will be E2. Okay, so as you are increasing the load, when the load is F3, as you are increasing the load, the extension would also be increasing. Okay, when the load is F3, the extension will be E3. So as you increase the load, the extension also increases. And that is what Hooke's law tells us. Though they will get to a point whereby the extension will no longer be proportional to the force, whereby you have a curved slope. Okay, so at that point when the extension is no longer proportional to the slope, to the force, you can say you have your limit of proportionality. That means the extension is no longer proportional to the force. Okay, you can name it the point X, and you call that point X your limit of proportionality. That is what happens when you keep stretching a spring and you stretch it beyond its elastic limit. You stretch it beyond its proportionality limit. Yeah, that means the force is no longer proportional to the extension. Limit of proportionality. Now, what happens if you stretch the spring beyond the limit of proportionality? You know, this is the limit of proportionality. If you stretch it beyond this point and you keep stretching, you get to a point which is the elastic limit. At the elastic limit, let's call it E. E is the elastic limit. At the elastic limit, the spring is no longer elastic. That means if you stretch it beyond that, it will just break. Now, what is the application of this? This is applied in in the case of objects that you need a shock absorber. For instance, let us consider the spring in your car. You can see this spring that is always very close to the tire. This spring is a shock absorber, and the thickness of that spring determines the stiffness. If the spring is as thick as this, then you know the value of K will be very, very high. Okay, that means K is very high. Yeah. So it means you need a very large force to cause um, unit extension. And if the spring is very narrow, as if it's as narrow as a strand of hair, that means little force will cause an extension. So that's the impact of the thickness of the spring on the value of K. Okay, of course, the value of K also depends on the nature of the material. So that is it. The shock absorber here, it really helps to stabilize your car. So if you have a car and you want someone goes into the car, what happens? This shock absorber here, the spring inside here, it acts as shock absorber and it makes the car to bounce a little. Yeah. Also, when you climb onto the bumps, if you are driving on the road and you climb on the bumps, this swollen, okay, or you drive into a pothole, you notice the shock absorber will make your car to bounce upward and downward a bit, and then trying to stabilize it so that you don't feel a sudden shock. So that's the impact of this spring. And the spring in your car, they are always thick when compared to the regular spring you see outside there. And the reason why it is thick is because it's bearing very large force. So the stiffness needs to be high. It needs to be very stiff. Okay. So all we are doing so far, we are just explaining the topic so that we can go ahead and start solving question, past IGCSE questions. So this is spring. And you can see this is another example of the impact of the stiffness of the spring on the force that we produce. Do not forget that a graph of extension against load looks just like this. What if we decide to plot a graph of extension against what if we decide to plot a graph of the length against the extension produced? What do I mean? If I put length here, in centimeter against the load, here we have the load in Newton. What kind of graph would we have? Are we still going to have a straight line graph that starts from the origin? No. We have a straight line graph that starts from L naught. The value you have here must be L subscript 0. Okay, the graph must start from when the length is 0. That means the length when no force is applied. Okay, then it will start going from your force F1 will produce an extension of your force F1 will correspond to the length L1. Also, your force F2 will correspond to the length L2. Your force F3 will correspond to the length L3. The point I'm making is that if you want to get the extension here, then you know the extension in this case, the extension E will be L1 minus L0. That will be the first extension, okay, when the force applied is equal to F1, okay. Also, if you want to get the second extension, it will be L2 minus L0, okay, and that will be the extension when the force applied is equal to F2. That is how you get extension. So a graph of the actual length against the load would be a straight line graph that the intercept on the vertical axis, this is the vertical axis of the graph, okay. The intercepts means where the slope hits this vertical line. That's what I mean by intercept on the vertical axis. And wherever it hits that line, that will give you the value of L subscript 0. That is the length when the force applied is 0, okay? And I'm talking about the original length of the spring when no force has been applied, okay? And L1 is the length of the spring when you apply the first force, okay? That's this length when you apply the first force, when you attach the